we present Flex, an extrinsic parameter-free multi-view 3D human motion reconstruction method.
The increasing availability of video recordings made by multiple cameras has offered new means for mitigating occlusion and depth ambiguities in pose and motion reconstruction methods. Here is an example where occlusion is solved by multi-view images. By combining wrist information from the left image and leg information from the right image, we are able to recover all joints. Yet, multi-view algorithms strongly depend on camera parameters, in particular, the relative positions among the cameras. Such a dependency becomes a hurdle once shifting to dynamic capture in uncontrolled settings. In the wild, we have only dynamic settings, as we can see here with the SkyCam.
We introduce Flex, free multi-view reconstruction, an end-to-end extrinsic parameter-free multi-view model. Flex is parameter-free in the sense that it does not require extrinsic camera parameters, neither rotation nor translation. We dub it EP-free.
Here we can see a human rig, observed via the relative access systems of 3 cameras. Our key idea is that 3D locations vary across access systems, while 3D rotation angles and bone lengths remain identical. And that is why fusing the former requires acquaintance of camera parameters, while fusing the latter requires none. We compare our model to state-of-the-art methods that are not parameter-free, and show that in the absence of camera parameters, we outperform them by a large margin, while obtaining comparable results when camera parameters are available. A known strength of predicting rotation angles rather than locations is the smoothness of the predicted motion. In this table, we compare the smoothness of our work against others. Smoothness is quantified by the acceleration error of each joint. Notice that our work leads the table by a large margin. Flex takes multiple video streams, learns to fuse deep features through a novel multi-view fusion layer, and reconstructs a single consistent skeleton with temporally coherent joint rotations. Our model is based on MotionNet, a state-of-the-art single-view motion reconstruction method. We use 2 encoders. The dynamic encoder, EQ, outputs a skeleton-independent sequence of 3D joint rotations, global root positions, and foot contact labels. The static encoder, ES, outputs a single, symmetric 3D skeleton represented by its bone length. We employ a discriminator that brings the temporal differences of rotation angles near the manifold of true rotations. The output of both encoders is used in a forward kinematics layer that computes the estimated 3D joint positions related to each view. These 3D positions are compared to the ground truth during loss computation. We demonstrate quantitative results on several datasets. Here, we show our results on the human 3.6 million dataset. The animation in the middle is reconstructed out of 4 video streams. Notice the smoothness and the naturalness of the motion. These are the results on the KTH Multi-View Football 2 dataset. Although this dataset is filmed by dynamic cameras and contains significant occlusions, Flex is still able to handle this more challenging setting. Notice how we do not miss the waving of the hand, even though it is occluded in the center view and blurred in the left.
Here are our results on synthetic data, generated to provide multi-person data with dynamic cameras. In such a difficult scene, the 2D backbone is often wrong, and yet, our method is capable of reconstructing correct 3D motion. Here are some examples. The head and left arm of the person wearing a black shirt are wrongly detected, but our algorithm reconstructs them flawlessly as seen in the animated reflection. The person wearing a red shirt is occluded by his friend, hence his estimated 2D pose is a clutter. Notice that the reconstructed red rig is correct.
Here is a comparison of the single-view baseline, MotionNet, with our work. Notice that while MotionNet is occasionally wrong, our model is accurate. Here is another comparison with Iskakov et al.'s work, which is the current multi-view state-of-the-art. They predict location rather than rotations. Hence, their reconstructed motion is prone to shakiness, while ours is smooth. In addition, one can notice inaccuracies in joint prediction, while Flex's predictions are accurate. Here are some more results. Thanks for watching.